You got that TV muted?
TV's muted.
All right. How do I usually start a video? What do I usually say?
1, 2, 3.
And then?
And then, hey guys, Lars here.
Correct. Or hey everybody, Lars here.
Hey everybody, Lars here.
All right, that usually works. All right?
All right.
Now zip it. Because I got to talk to these guys and teach them about recursion. All right? Mm-hmm. Good job. Put your headphones in. Go play Minecraft.
Wait, we're still recording?
Yeah, we're still recording.
Oh, okay.
Don't worry about it. You're going to be famous. Not. Hey everybody, Lars here. As I always say, life happens, so I'm down at my sister's house in Mount Laurel looking after my dippy nephews, but I did not want to let that stop me from quick doing a recording and showing you some stuff about recursion, because it's the last part of Unit 4, and Unit 4 doesn't have a lot of life yet, but I'm going to extend it for you. We'll talk about that at the end of the video when I do some announcements. But right now, we're going to take a look at recursion. Like, what is recursion? I loaded some stuff up. We'll take a look. As always, we can run to Wikipedia and read about recursion, what it means. Recursion is actually an interesting topic as far as language, art, but we're going to look at it as far as recursion is concerned with computer science, art, the works of Escher, if you know about Escher. There's an Escher in Lego. So recursion is self-referential, and a lot of different fields deal with it, but we're going to deal with recursion in a computer programming sense. And in a computer programming sense, basically, I got a little playground area ready for us to go. When we first see recursion in a computer science sense, it's basically a function that refers to itself. And I'm going to really quick do one, and then we'll take a look at it. The secret to it is recognizing problems that are just repetitive steps over and over again with a smaller subset of what you're looking at. And that sounds a lot more sensible when we have a definition. So let's define a function, and we'll call it my sum. And it will take an integer n. And if I take that integer, I check to see if n is 1. And we'll see why in a second. And if it is, I merely return 1. Now, if it is not, I return, not retrun, I return n plus, and then I call the function again. But this time I do it with n minus 1, so it's 1 smaller, okay? Now let's use it. So I say a equals my sum, let's say 7, and then I print a. So what should I get? My sum is a function that gives me the sum of the number 7 all the way down to 1. So it'll be 7 plus 6 plus 5 plus 4 all the way down to the end, and I think that is 28. Let's find out. Yay, worked the first time. So we have a function that I give it a number, and it gives me the sum of all of the numbers down to 0. Now, how does that work? Let's trace through some of the code. I get my sum of 7. So my sum comes up here with 7. Is n equal to 1? No, it's equal to 7. So I go to else, return 7 plus my sum n minus 6. So that 7 sits there, and I call my sum again. Now, and we're going to do this in a second with another drawing, but basically what people do when they have a mental model of recursion in their mind is they say, okay, this is still my work area, and they come back up here again. And what they don't think is to go grab yourself another copy of it and consider it blank. This return 7 plus my sum 6 sits out in space, and a new version is called over here. So my sum n is done with 6 is equal to 1. No. So else return 6 plus my sum 5. Okay? Then that sits out there. Then I call it a third time. And this time is n equal to 1. No. Else return 5 plus my sum 4. And it goes down the line until finally n equals 1. And then I return 1. So when I return 1, to what called it beforehand, it'll say return n plus 1. N will be 2. So then I'll return 3, and it'll get returned to the former one, which was 4, which then was 5, 6, 7. You see? That's called going back up the stack. And when we do the drawing I'm going to show you in a second, hopefully you'll understand that a little better. So if I do just a simple example with 3, and we run that, and you see we get 6. I gave it 3. Is it 1? No. Return 3 plus my sum 2. What's my sum 2? Is it 1? No. So return 2 plus my sum 1. Is it 1? Yes. I return 1. Plus 2 is 3. Return 3. Back to return 3 plus that. So 3 plus 3 is 6, and that's the answer. All right. It's going to be easier to see in a moment. The thing to remember is that this is the key to the operation right there, that plus sign. By just changing this plus sign and making it say multiplication, we instantly take that MySum function and make it factorial. See, when I run it now, I get 6. Oh, that's interesting. Same thing. But if I ran it a 7 here, you're going to get 5040 now. Okay, you're not going to get 28. If you run 5, I believe you're going to get 120, and so on down the line, because now this is factorial. You should, actually, so you don't confuse people, change the name. But the point is, that's the operation right there. You have a list of things that you have to do, and you recognize that it's the same operation, just on a smaller subset of the list going down. So you can do something like MySum, and then you can do something like factorial when you do recursion in computer science. Now, when you do recursion in programming, keep in mind it's not like you're just loading and loading on top of this workspace so it gets all convoluted in your brain. Just think of it as taking another fresh copy of this function and using that. Because in fact, that's what's happening. That's how the computer and the compilers handle that, is that you're just grabbing a fresh copy of that function, bringing it out, and using it. Okay? Now, what I usually do, and I think I told you this in the slides, is I want people to see something familiar done in a recursive fashion, because when we do Fibonacci, and sometimes when we do factorial, people have never seen that before. So when you do it recursively, it's no big deal. It's the first time you've ever seen it. I want to do something you're familiar with and solve it in a recursive fashion. And what I usually do is I show people multiplication. So I have this little piece of code here. I believe these were in your slides as well. And what I do is I implement multiplication recursively. But I could go through what we just went through before, but I like to trace the code this way. Hold on. I think I got something ready for us. Bang. I love it. Okay. So I'm going to call, if you remember, I'm going to call my mult 3, 3. And then I'm going to print the result when the result comes back. So 3 and 3 map to num and times. So what happens when I come in here? Num is a 3. Oh, hopefully I can draw this well. And times is a 3. Is times equal to 1? No. So return num, which is 3, plus my mult num, which is 3, times minus 1. What's times? 3. So minus 1 is 2. Okay? So what this operation right here, what is that? That's right down here. We got a fresh copy. Okay? So now we have a fresh copy. So num is 3. Times is now 2, because that's what we called it with over here. So times is 2. All right. Is it equal to 1? No. Else return num, which is 3, plus my mult, 3, times minus 1. Times is 2. This time it is 1. Okay. Oh, that's a bad one. Should I do undo? What will undo do to me? Oh, good. It'll only get rid of that 1. Okay, 1. All right. So my mult is called again. It's this one down here now. Just a blank copy. So num is 3. Times is 1. Is times equal to 1? Yes, it is this time. Check. So return num. So now I return the value. So the value of this entire call here is 1. Oh, no, I return num, so I return 3. I was going to say that wouldn't work very well. So it's 3. Okay? So now what do? Now I can return. This is back. Num3 plus 3 equals what? 6. So what do I return to the call up here? 6. Okay. So this whole thing now equals 6. All right. This is looking messy. I've done this in the past and it was equally as messy. So now I can return num plus 6. So num is 3 plus 6, the value 9. Okay. So if I run the beastie, there you go. I get 9. And that's pretty much what happened when we ran it. Just when you think of recursion and you're calling a function within a function, it's self-referential, it seems weird, but it's not. Just think of yourself as grabbing a fresh copy, okay? That's all it is. So when you examine problems, factorial, my sum, the exponent problem we gave for homework, wink, wink, nod, nod. I mean, think about what exponentiation is and how that operation goes down. Is it something that can be reduced to something smaller? So multiplication is something like that. When you get more sophisticated, you can start looking at things like doing sorts in a recursive fashion. I know I'm going back and forth with Danica about the anagram example that was in Zell. So there's different things you can do with recursion, and there's different ways to utilize it. The reason we do it in computer science, for the most part, is when you get more sophisticated, you're going to learn about binary trees. You're going to learn about binary trees in Unit 6. I'm going to introduce them to you. But you're going to find out that when we store data in binary trees, recursive operations work very well in tree structures. Because what do you have at the side of a binary tree? Another binary tree. And what are binary trees composed of? Smaller little trees. So it works, recursion works very well in a lot of different ways as far as how we store data in computer science. And you're going to see that as you get more sophisticated and you move on. So I wanted to make sure I introduced recursion and let you see it, because as far as computer science topics are concerned, it's pretty important. And you'll see it'll get used, and you'll see it gets easier. It's like anything else. It's exposure and experience, and you're going to be fine. So do not let it freak you out, okay? When you're tested, I'm not going to test you on 50 different recursion things and make you find recursive answers for different things, all right? So do not worry about it. All right, so that's it. That's recursion. That's the recursion video. I wanted you to see a couple of examples. I wanted you to see the multiplication diagram as I traced through the code and went down the stack and then back up the stack with the operation, okay? If I'm not mistaken, now you have all the materials for Unit 4. You've got your 2 review videos. You've got your homework assignments. You've got your slides. You've got your Zell readings. We meet in person next Monday night. But as the syllabus says, that should also be the end of the unit. I'm not going to end the unit on the 28th. I'm going to push it 2 days, and I'm going to give you your quiz on the 30th. I think if you look at the homework assignments, I didn't even make them due until like April 2nd or something like that. I think that's the case. I'll go back and double check. So we're going to have the quiz on the 30th, and then I'm going to begin Unit 5 either that Thursday or that Friday. I want to get started on Unit 5 because Unit 5 is important. It's about object orientation. It's a 3-week unit, and I don't want to shortchange Unit 6 that much. And I looked at the syllabus real quick, and I saw that I get you guys out of Dodge like around the 2nd of May, so you have ample time to work on your final projects. Don't forget there's a due date coming up for that proposal for your final projects too. So make sure you get together with your group mates and you start talking about your final projects and what to do. In the next couple days, I will probably be killing you with announcements every day and sending out email reminders to remind you of what projects are due and what projects aren't due. Okay? So that's the recursion video. That's my story, and I am sticking by it. Keep chugging along. Everybody's doing great, and I will see you. I'll be sending emails over the weekend and getting you used to things, and I'll see you guys on Monday night. All right? You be good. I'll talk to you later. Bye.